Hi, my name is Alyssa Freeman, and I am a PhD student in the Math and Science Education Research Program. Today, I'm presenting some preliminary findings we have for a project regarding graduate teaching assistants, or GTAs, and their perceptions of their teaching autonomy and pedagogical discontentment in different STEM disciplines. Teaching autonomy refers to the GTA's perceptions of their control or ability to make decisions in their teaching position. Pedagogical discontentment refers to the dissatisfaction the GTAs have with their teaching. Our proposed conceptual model suggests that in order for GTAs to experience dissatisfaction with their teaching, they must perceive having some autonomy in their role. The dissatisfaction could then lead the GTAs to seek out and engage in professional development opportunities, which could increase their teaching quality. In the context of this project, we are interested in exploring the GTA's perceptions of autonomy and discontentment to test our conceptual model. Specifically, we gave GTA participants surveys so we could describe their perceptions of their control and dissatisfaction. We were also interested in exploring any differences in their perceptions among the different STEM disciplines, and we specifically looked at biology, chemistry, geology, and mathematics disciplines. To show our findings for these research questions, I've included violin plots on the slide. The left plot is for autonomy, and on this plot, the higher number on the y-axis indicates lower perceptions of autonomy, while the lower numbers indicate having more autonomy. Our results show a median between 2 and 3 for the GTA's autonomy level, indicating they perceive as having some autonomy. We then ran an ANOVA to determine if there was evidence of a difference between the GTA's autonomy perceptions amongst these different disciplines. The results indicated that biology GTAs perceive having lower autonomy compared to the mathematics GTAs who perceive as having higher levels of autonomy. The right violin plot is for a result of the GTA's dissatisfaction with their teaching. In this plot, the higher numbers on the y-axis indicate higher perceptions of dissatisfaction, while the lower numbers indicate higher levels of satisfaction. And our results indicate that the GTAs have a median of approximately 2, so they are pretty content with their teaching. The ANOVA results for the dissatisfaction indicates that there is not a difference between the GTA's perceptions of their dissatisfaction based on their discipline. And we are currently in the process of interviewing participants to be able to obtain qualitative data and a deeper understanding of how these ideas are related to be able to update our conceptual model. Thank you for listening.
Collaboration can help us obtain different ways of understanding that lead to insights and a more complete vision of any problem at hand. These insights, alternate views of problems, and creative solutions are particularly important in mathematics, as mathematical discoveries help shape many parts of everyday life, including technology, medicine, finance, national security, and many more. Yet, unfortunately, creativity is often undervalued and de-emphasized in undergraduate mathematics, and there's evidence many mathematics assessments require only memorization and algorithmic reasoning. It's for this reason I've dedicated my dissertation research to better understanding how undergraduate mathematics students experience creativity through collaboration. I collected student-written reflections from an undergraduate Introduction to Proof course in which students described when and why they felt creative during in-class collaborative proving exercises. To analyze my data, I first sorted all the sentences written in the reflections as describing feeling creative or not feeling creative. Then I carried out an inductive analysis and developed 13 themes describing their experiences. When reviewing these data, I was astounded that the most frequently emphasized element of collaboration students associated with their creativity was when students made mistakes, felt uncertain, or took a risk they were unsure would pay off. Even more surprising is the fact that students did not see making mistakes or feeling uncertain as hindering their creativity. The power of mistakes opening the door to creativity is best illustrated by one incident I witnessed in this course. A group of students were attempting to prove a statement regarding twin prime numbers, so they first began to verify the statement with examples, 5 and 7, 11 and 13, all the way up to 51 and 53. However, later in their proving attempt, the group realized 51 is not prime at all. This mistake allowed the team to make a conjecture that the statement that they were trying to prove was true not just for twin prime numbers, but for all numbers. This interaction was so powerful that a student in a different group wrote in their next written reflection the following: On the same day, there was a second eureka that mistakes can turn into miracles. In another team, there was a mistake in claiming that 51 was a prime number, and the formula still worked. Living through these moments is the exact reason why joining multiple people together to solve a conjecture can prove more efficient than working in solitude, as more ideas, dare I say, mathematical creativity, flow through the atmosphere, allowing multiple standpoints and views on a conjecture to be fleshed out in an extremely positive way. Learning that students can and do experience collaborative creativity in mathematics when they make mistakes informs the way instructors should be facilitating activities to foster creativity. No matter how hard it may be to want to correct students and get them on what you believe to be the best path, take a step back, trust the process, and let the students lead the way. Then when they get to a correct result, it will be that much more satisfying.
Ask the question, how do science leadership programs empower informal science teacher leaders? I ask this question because of the lack of information about how science teachers develop their leadership skills and abilities, and also because national programs in the United States advocate for science teachers to be leaders in order to innovate and reform science instruction. Science teachers attend science leadership programs, and it's in these leadership programs that they develop their awareness, their knowledge, and skills of leadership, and they become science teacher leaders. As science teacher leaders, they can occupy positions outside the classroom in administrative roles like a science coordinator for a district. But the science teachers I'm interested in are the informal ones, those that work with students in the classroom. They are still classroom teachers. In addition to working in the classroom, they also collaborate with their peers, participate in decision making, they serve as mentors, and they impact students in other classrooms. These informal science teacher leaders do not have an administrative position or job title, and they are seen as being very effective in working with their colleagues because they share the same job responsibility of teaching students. These informal science teacher leaders need to be empowered. They need training that allows them to learn how to develop influence through their relationships. They need to be motivated, they need to develop confidence, and they need to develop autonomy in selecting their work activities. I examined 10 science teacher leadership programs from 2017 to 2023 in contexts throughout the United States with about 400 participants. Using a lens of leadership empowerment, I determined that enhancing instructional and content knowledge of teachers allowed them to feel empowered. They develop confidence by being able to address their misconceptions about science through science lessons, through teacher presentations, discussion with their colleagues, and reflecting on knowledge. And they were eager to share that knowledge with their peers. They were also empowered by developing leadership through collaboration. They went through a progression of leadership positions, and they were mentored as well as mentoring others. They learned the value of teamwork. Knowledge and collaboration are two elements that will inform program development for science leadership programs, which is one of the impacts of my research. The ultimate impact, however, is to maximize student achievement in science.
My name is Chance Perkins, and the research project I'm working on, we study the effects of microplastic contamination on the biogas production of anaerobic digestion of solid food waste. And this is an important study because in the United States, we create 60 million tons of food waste a year, and 56% of that food waste is sent to landfills. And that presents a huge problem because inside of a landfill, food waste breaks down anaerobically, and it can create and release methane gas into the atmosphere. And methane is a very potent greenhouse gas, and it's much more potent than carbon dioxide. And 16% of all methane emissions in the United States originate from landfills. So if we lower the amount of food waste we send to landfills, we can decrease methane emissions from those landfills. However, we need a useful technology to divert food waste from landfills. Anaerobic digestion is a very great technology we can use for that. So an anaerobic digester works by heating an enclosed container that contains organic material and a diverse microbial population to break down that organic material. Using an anaerobic digester instead of a landfill to dispose of food waste has a few net benefits as well. So one of the big benefits, obviously, is decrease in greenhouse gas emissions. The other benefits are the byproducts of the digestion process. The first byproduct is called biogas, and biogas is a collection of different gases that can be used as a combustion fuel source, and it's renewable. The second byproduct is called solid digestate, and that is very similar to compost, and it's the solid remainder after the digestion process and can be used as a soil amendment. A problem we face in the digestion process, though, is microplastic contamination. So microplastics are plastic particles between 5 millimeters and 1 nanometer in size. They've received a lot of attention in marine environments. However, they have not received as much attention in terrestrial environments, where they're also a huge problem. And microplastics have been demonstrated when they contaminate microbial growth media to have negative effects on microbial populations. And this is important because microbial population health and diversity is a key indicator in the performance of an anaerobic digester system. So if the population of microbes is not healthy and robust, the performance of the anaerobic digester will go down. In our lab experiment, we have designed a series of anaerobic digesters that are loaded with solid food waste, bacterial inoculum, and differing levels of microplastics. And these microplastics vary based on size, total weight, and polymer type. And we are testing the biogas produced by these digesters and analyzing it via gas chromatography and Fourier transformed infrared spectroscopy to understand the effects of the microplastics on the biogas production. This research is ongoing. However, our early results have shown a decrease in total biogas and a shortening in the time frame that biogas is produced, and we expect to see further metrics indicating a decline in anaerobic digester systems when the contamination levels of microplastics increases. Thank you.
My name is Christopher Clark, and I am a second-year MOBI PhD student in Dr. Subik's Energy Lab. My research is focused on the development of novel ferrugulin analogs that act as colchicine binding site inhibitors for the treatment of metastatic melanoma. Metastatic melanoma is a type of skin cancer which is known to be extremely aggressive with a high mortality rate, and it's hard to treat. Currently, treatment of this cancer is done by the destruction of cellular processes such as the destruction of microtubules. Microtubules are long chains of alpha and beta tubulin, which rapidly polymerize and depolymerize when they are needed for important cellular processes such as mitosis. Disruption of microtubules can cause a disruption in mitosis, which can then halt the spread and survivability of melanoma cells. Ferrugulin is one such compound which can cause this destruction. It accomplishes this by binding to the colchicine binding site, a region between bonded beta and alpha tubules. Binding to the site makes the microtubule unstable and causes it to depolymerize. Inhibitors such as ferrugulin, which bind to the colchicine binding site, are unique compared to other microtubule inhibitors in that they are immune to several types of drug resistance that other inhibitors are susceptible to. Despite being so potent, ferrugulin failed in clinical trials due to unforeseen toxicity. Because of this, there is a need to develop new series of compounds with new properties and less toxicity. I've synthesized 22 new compounds based off of ferrugulin and have tested them against A375 melanoma cells through an MTC assay. This assay shows the effect my compounds have on the growth and survivability of cancer cells over a period of 72 hours. I've shown that my compounds have a dose-dependent effect on the activity of these cells, and I've been able to find the concentration of each inhibitor to be a 50% effect, the GI50 value. In summary, 11 of my compounds have notable submicromolar efficacy, and 2 of my compounds, R9 and R17, have been confirmed as tubulin inhibitors with sub-100 nanomolar efficacy, which is pretty potent. To complete this research, I'm further characterizing my compounds' effect on cancer cell proliferation, metastasis, and in vivo efficacy in a tumor xenograft mouse model. I apologize that I cannot show the structure of my new compounds in this presentation, but they can be shown once my work is published. Thank you.
In science, it is easy to trace how the development of tools has revealed things that are difficult to see. The invention of the microscope contributed to our knowledge of cells. Telescopes allow us to see stars and planets. These tools have been essential for building and advancing our body of knowledge. But what tools are available for teachers to make judgments about students' thoughts that are impossible to see? How do we identify what students know or understand? For years, students' knowledge has been observed using assessments that indirectly measure the ideas and skills associated with what students know. But like improvements in the microscope and telescope have revealed the complexity of our universe, advances in assessment strategies are important. Better tools allow teachers to explore learners' development as they move from novice to expert. Accurately measuring what students think, know, or understand is a challenge, and this challenge is compounded when we think about interdisciplinary ideas. My work aims to address this contention by using construct measurement to develop assessments that reveal to teachers how effectively students integrate the knowledge and skills gained across science and mathematics. For example, in most K-12 schools, students are expected to master the fundamental ideas about data analysis and data modeling in mathematics classes, but these skills are essential across many disciplines. In fact, conversations about data collection and analysis are usually associated with science inquiry. In addition to understanding core content and disciplinary practices in science, students at every level need to make decisions with data. One result of the siloed approach is that students are responsible for building interdisciplinary connections without direct instruction or substantive feedback, because current assessment tools usually focus on one subject. My research has resulted in tools that help middle school teachers support students' construction of stronger connections between knowledge of statistical variation that they build in mathematics classes to the scientific context of their data. Using Mark Wilson's framework for constructing measures, I began by mapping the development of student thinking about variability. Then I developed items based on the progressive levels. Now, we can not only assess whether students correctly identify a point on a graph, but can compare their response to the predicted progression of noticing qualitative differences, measuring those differences, creating a distribution, and ultimately comparing models for the same distribution. This type of assessment gives teachers a more complete representation of each student's level of learning. And when teachers are equipped with better tools for revealing what is difficult to see, they too can better understand and improve their knowledge of and about their students.
Dipolar cycloaddition is a very important method of forming ring structures in organic chemistry. A dipole is a group of atoms whose electron density is unevenly distributed. If we combine a dipole such as this one with a carbon-carbon double bond in the presence of a base, then we found that we can form this 5-membered ring with 2 nitrogens in it, which we call a pyrazole. This is a relatively easy process where in only a few steps we can form a pyrazole from products that are readily available. The dipole that I used was a diazoalkane, which is depicted here, and the double bond that I used was in the arone, which is a naturally occurring compound in some yellow flowers. I was able to synthesize 8 unique novel compounds by changing the substitution of this aryl group here. Arone derivatives such as pyrazoles are known to have medicinal properties like antiviral, antibacterial, and antitumor. But they also have pretty good membrane permeability, and they display fluorescent effects. Fluorescence happens when a compound absorbs energy at one wavelength and then re-emits that energy at a characteristically different wavelength. So you can see how it would be useful to deliver these compounds to a specific target through good membrane permeability and then analyze them using their fluorescent properties. So I did a solvent study in 12 different solvents, including water. And water usually quenches fluorescence, but in some cases I found that the fluorescence was actually increased as compared to the other solvents. So going forward, I would like to create more unique pyrazoles and do the solvent study with them so that we can better understand the interaction with the solvent that leads to this increase in fluorescence.
Hi, my name is Joshua Tamatong, and I'm currently enrolled here at MTSU as a master's student studying chemistry. I am also currently part of the Banerjee Research Group, and what I do over there, at least a little bit of my work, is help design and develop colchicine biocide inhibitors for cancer such as neuroblastoma. Now, to kind of go a little bit back on the history of my research, I want to talk a little bit about tubulin. So tubulin is this large protein network that is made up of these smaller subunits called microtubules. And these microtubules tend to kind of stack together in a head-to-tail fashion that, when you combine them all together, make up this cylindrical tube that is what tubulin is. And so the reason we want to design colchicine binding site inhibitors is because colchicine, the binding site itself there, has a property where there's just less drug resistance overall. And so when we design a compound over there, we hope to have that same properties there. And so what we did on figure 2 was, of course, make some of these compounds that fit inside the colchicine binding site. And what we noticed was that some of the parts of our compound tended to interact with both the alpha and the beta subunits inside the colchicine binding site. And so we saw this as a good opportunity to say, hey, if these are binding here and interacting with these subunits, let's take it to a computer simulation and see how long they last. Well, the good news is during that computer simulation, which is figure 3 here, our compound stayed within an RMSD value of 1 to 3. The good news here being is that since it was within that range, our compound inside the binding site tended to stay inside the binding site overall, which was a good sign for us. So from there, we then designed a few of these different analogs, and one of the analogs included this methoxy group, or the OMe, as I say. And we also designed compounds that have chlorine in them as well as fluorine in them. Well, what we saw was that the best compound we'd have there was this trimethoxy group that had a GI50 value of 8 nanomolar, which is very good inhibition, almost mimicking the effects of colchicine. Since we saw that, we then took it to a in vitro assay that showed us, yes, it was actually mimicking the effects of colchicine and binding nearly just as well as colchicine. So from there, we took it to a cell assay, cell cycle assay, and then saw that, yes, not only was it mimicking colchicine, it was also arresting cell cycle, which is very good for us. What does this mean for neuroblastoma, though? Well, neuroblastoma is a type of cancer that wants to kind of have uncontrolled cell cycles, right? So we saw that our compounds can mimic the effects of colchicine, which itself is very toxic, and kind of do better on it. And so what we hope to do is develop better colchicine binding site inhibitors overall. Thank you.
Have you ever felt unprepared to have conversations about topics more controversial than pineapples on pizza? We're talking about things that go past the dinner table into society. So things like climate change, vaccines, and evolution, which are 3 examples of what we call culturally controversial science topics. Ones that most scientists agree on, but are highly controversial in the public. Even though they're controversial, discussions about these topics, especially vaccines and climate change, have pretty big implications for all of us, so how we talk about them matters. For example, the way that scientists communicated about COVID-19 affected how the public perceived both the severity of the illness and the safety of the vaccine. Right now, you might be thinking, oh, it's just the scientists and the people in the government having these discussions, right? Well, our research shows that undergraduate biology students, including our own students right here at MTSU, are having these critically important conversations about climate change and vaccines, yet they don't feel prepared to have them. This led us to ask, how can we train our undergraduate biology students to communicate effectively about these culturally controversial science topics? What we're doing to try to support these students is implementing a short science communication module in our introductory biology class. We're focusing on introductory biology because these courses represent the most diverse pool of identities and career paths, so these are students who may become scientists, doctors, or even government policymakers. In this science communication module, our students learn what a culturally controversial science topic is, then are asked to write down what they would say to someone who didn't believe that humans are involved in causing climate change. Then they're taught about what's effective and ineffective science communication and asked to revise their previous statements. Finally, students are asked to transfer their knowledge of science communication to a new controversial topic, vaccines. So we wanted to know, Did this science communication module affect their real-world communication? After students came back from their summer break, our undergraduate research assistants interviewed them about their science communication experiences after instruction and if they were able to use the skills they were taught in conversations after the course ended. Before the module, students tended to rely heavily on facts and statistics and often got emotional and had arguments instead of conversations. After the module, what we've seen so far is that overall, students have been able to use what they've learned to have more productive discussions with their friends and family. For example, one student said that they were able to have a dialogue with their grandmother that resulted in her getting the COVID vaccine after 2 years of her being unvaccinated. Multiple students have also stated they feel more confident in their abilities to have these types of difficult conversations, and some students have also stated these skills will be useful to them in their careers while they be, for example, interacting with patients. We're incorporating this module into our course again this fall and planning on gathering even more data to help us improve the impact of our science communication instruction. We'll be examining student responses to the in-class assignment to see how student use of effective and ineffective science communication changed prior to and immediately after instruction. Then we'll be interviewing even more students from this semester after their winter break. This will allow us to continue evaluating and refining our instruction, and we plan to eventually be able to publish this evidence-based instructional practice so that more instructors can have the tools they need to train our next generation of scientists to be effective communicators about controversial topics.
All right, you've probably heard that the Nobel Prize in Chemistry was awarded to 3 researchers for their discovery and development of quantum dots. A lot has happened in this field since Alexei Akhimov discovered that tiny particles embedded in glass were responsible for its unique optical properties. And at about the same time on the other side of the world, Louis Bruce discovered that you could change the color of these particles by changing their size. But before we get into any more of that, you probably want to know what these quantum dots are used for and what exactly they are. Right now, you're watching this video on some sort of display, and it's possible that display has quantum dots inside of it. These materials are also very promising for developing super efficient solar panels. Now, these are just 2 of the many examples I could give that span a very wide range of applications. However, despite their discovery more than 40 years ago, there's still a lot we don't understand about quantum dots. In particular, some of that mystery lies right on the surface of these particles themselves. Briefly, I'd like to explain what quantum dots are, which will bring me to the contributions of our 3rd Nobel laureate. Quantum dots are nanoscale-sized particles. In fact, they are so small, the image at the bottom left of the slide was taken by zooming in 600,000 times using an electron microscope. These particles consist of inorganic cores composed of semiconductor metals that have molecules bound to their surface, which we call ligands. These ligands compose the chemical aspects of quantum dots and are responsible for various types of reactivity, and possibly most importantly, their colloidal stability. And a colloid is a suspension of insoluble particles. It was Manji Buwendi that developed the method for synthesizing these materials in a way that allows us to make uniform distributions of quantum dots, which set in motion our ability to harvest and apply the powerful properties of these materials to the applications I mentioned before. Now that's what has happened, but let me tell you about what is happening here at MTSU. I use a method called direct analysis and real-time mass spectrometry, or DART-MS, to characterize quantum dot surface chemistry. If you are unfamiliar with mass spectrometry, in short, it is a method used to identify molecules based on their masses. DART-MS is unique to other methods because it is what we call ambient air ionization, which allows us to analyze samples without the need of oxygen-free vacuum-sealed environments. Additionally, the method is quick, requires minimal sample preparation, if any, and only uses a small amount of sample. I use this method to directly analyze the surface chemistry of quantum dots. I'm investigating things like what ligands are actually bound to the surface, how many of these ligands are there, and other physical properties related to the interactions between ligands and the inorganic cores. This method is allowing us to advance our knowledge of quantum dot surface chemistry, which will lead to improving the materials for applications down the road. Thanks.
How can we increase people's acceptance of topics that are controversial in society but not to scientists, like climate change and vaccine safety? Some researchers have argued that increasing people's understanding of these topics should be enough to sway them, but many others have uncovered that having a high understanding of these topics is not always associated with higher acceptance of them, since other factors besides understanding, like political or religious identity, can also influence decision-making. I wanted to explore how religious identities impact students' views on another topic controversial in society, evolution. Do college biology students' religious views impact the relationship between their evolution understanding and evolution acceptance? Biology students are a unique population because many will become biology teachers, doctors, and researchers, meaning they'll be more likely to need to apply their evolutionary knowledge to solve new problems in their futures. But it's unlikely they'll utilize their understanding of evolution to solve these problems unless they accept that evolution is true. To answer our research question, we surveyed over 11,000 college biology students across the country. We asked many questions to assess their evolution acceptance, their understanding of the theory of evolution, and how religious they are. To clarify these results shown below, the x-axes show the percentage of evolution understanding questions answered correctly. On the y-axis, 1 represents very low acceptance, while 5 represents a very high acceptance. And the different colors represent groups of students with different religiosity levels. For example, green shows highly religious students. In general, we found that higher evolution understanding was associated with higher evolution acceptance. However, this relationship was significantly weaker in religious students compared to non-religious. Our most notable finding, in highly religious students, there was no relationship between students' evolution understanding and their acceptance that all life on Earth shares a common ancestor, a concept supported by the theory of evolution. These two findings suggest that increasing students' understanding of evolution alone may not be enough to promote evolution acceptance in all students. So, if students understand what we teach them, why care what they believe? Well, when we have students that don't accept the evidence for evolution, even though it is so robust, that tells us they may need more support in evaluating topics they perceive as controversial. One strategy to address this involves incorporating inclusive research-based techniques that address the various identities students hold in addition to teaching the facts, so that students are supported to apply their evolutionary knowledge when presented with new problems. Thank you.
Hello everybody, my name is Mary Ade and I'm here to talk about my research. Based on existing literature, the issue of safe and effective administering of medicines to children has been a prevalent problem in the pediatric healthcare industry. Therefore, my research seeks better ways to give medicine to children. We want to make sure it is safe, effective, and good for the environment. Think of it like designing a special system that works well for kids, using materials that are eco-friendly and making it easy for both the children and doctors to use. This does not only help kids get the right medication at the right time, but also contributes to our planet Earth. Therefore, the objective of my research is to improve how we deliver medicine to children, making it effective, safe, and eco-friendly. There are 3 research questions that the ongoing project seeks to answer. Firstly, how do we make effective medicine for children and ensuring it won't cause any harm? Secondly, what can be done to ensure administering meds is easy and also environmentally friendly? Thirdly, why is it crucial to consider the needs of children when developing medicines and incorporating sustainable practices that will benefit both the children and the environment? The research methodology for this ongoing project involves literature-driven approach, basically reading and understanding what others have already studied. This can be books, research papers, journal articles, to figure out what is really important. Also, to explore patient needs through literature review and distill key requirements to guide subsequent design and development phases. The impact of the research is like building a superhero medicine system for kids. Like we all know, kids love cartoons. It ensures when children need medicine, it is not only super effective but also really safe for them. Likewise, it's like giving a gift to our planet because we're making sure the way we provide the medicine is friendly to the environment. So it's actually a win-win. Healthier kids, a healthy planet. Furthermore, the impact of the research can be subcategorized into 4, such as healthcare advancement, environmental stewardship in healthcare, innovation in pediatric medicine, also bridging the gap between pediatric medicine and sustainability. Thank you.
Hi, my name is Mary Tran, and I'm thrilled to present my project titled A High-Throughput Screening Approach to Discover New Antimicrobial Peptoids Against Staphylococcus aureus. Antimicrobial resistance has been a rising problem worldwide. This global escalation is causing a surge in infection with limited treated options. Staphylococcus aureus is one of the most prevalent gram-positive bacterial pathogen that is the primary cause of skin and soft tissue infections. They are notorious for developing resistance towards antibiotics, which pose a severe threat, particularly to immunocompromised individuals. In 2019 alone, Staphylococcus aureus contributed to over 100,000 deaths. And some of the factors contributing to antibiotic resistance is overuse and misuse of antibiotics, the unnecessary antibiotics in the agriculture and livestock, poor hygiene and sanitation practices, especially in the hospital and clinic, and then the lack of new antimicrobial agents. Proposed here are efforts to discover antimicrobial peptoids effective against Staphylococcus aureus using a high-throughput screening method termed the Peptoid Library Agar Diffusion, aka PLAD assay. This method is an innovative and rapid way to screen combinatorial peptoid library on a chemical cleavable PLAD linker against a microbe of interest. The PLAD linker consists of two identical strands, referred to as the alpha and beta strand, indicated here with the red and blue. Within the screening, we have this cocktail mixture of peptoid beads, Staphylococcus aureus, and TSEP, which is a reducing reagent that allows the diffusion of only one peptoid strand into the screening. And the evaluation of the plate the next day help identify peptoids with significant zone of inhibition, termed HITS compound. We're able to then cleave the other peptoid strand using the cyanogen bromide, which we would then attempt to deconvolute the structure using tandem mass spectrometry. Following deconvolution, we will proceed to resynthesize the promising peptoid. These compounds will undergo rigorous biological testing, determining their minimum inhibitory concentration against a spectrum of bacteria, and assessing their cytotoxicity against various mammalian cell types. Through this endeavor, our goal is to contribute novel solutions to the global challenge of antibiotic resistance and addressing a critical need in the field of infectious disease. And thank you for your time.
Hi, my thesis is about a pure math topic, which is a challenge for me to explain it in 3 minutes to an audience with different math background, but I tried my best having some picture. So it is well known that there is an incidence poset associated with every direct graph. Now, having this incidence poset, we get a direct graph that's non-isomorphic to our original one, yet it shares the same incidence poset. And then the problem that arises here is that the incidence poset does not encode enough information to recreate our direct graph. So this problem is solved by considering tripartite posets whose middle elements covers and exactly covered by one element, and which possess a bijection between the maximal elements and then the minimal one. And then the beauty of this method is that by specifying the bijection, we get an object that uniquely determines the direct graph associated with it. So it is no great surprise that the category of digraph with digraph morphism is equivalent to the category of digraph posets with digraph poset morphisms. So what we did is that we extend this idea to lattices, and we build a dual categorical equivalence between the category of digraph poset and then the category of digraph lattices. The object in our new category are finite distributive lattices where the joint prime element of it is a digraph poset and which possess a map called meta-vertex map. So as you can see here, the joint prime elements in red is a digraph poset, And we define the meta-vertex map in a way such that the restriction of the meta-vertex map to the joint prime element is a vertex map. So now that we establish a categorical equivalence between the category of digraph and then the category of digraph poses, and we also have a dual categorical equivalence between the category of digraph posets and the category of digraph lattice, we've established a dual categorical equivalence between the category of digraph and then the category of digraph lattices. Thank you so much for listening.
Hi everyone, my name is Teresa Ayangbola, and today I'm excited to share a glimpse into my research on science identity development among first-generation college students in science classes that use learning assistants. First-generation college students are those whose parents did not earn a baccalaureate degree, and unfortunately, this student group faces marginalization within science discipline. So why does science identity matter? Science identity has been proposed to increase persistence in science, especially for marginalized students. Therefore, for first-gen students, developing a strong science identity can be a game changer in their persistence, retention, and completion of their science degrees. Now let's talk about the setting of my study, the LA supported classes. Learning assistants or LAs are undergraduates who facilitate learning and classroom engagement. LAs are crucial in creating a supportive learning environment. So I studied introductory biology and chemistry classes that uses learning assistants, and this context becomes the canvas for exploring science identity. So how did I explore this? By employing qualitative methods, I interviewed first-gen students in this classroom to really uncover their unique experiences, focusing on science identity development. And what did I find? The stories of these students are rich with insights. Patterns emerge, revealing how the supportive learning environment provided by the LAs created one, valuable social learning experiences, two, a sense of belonging, and three, how this verbal recognition boosted their attitude, all contributing to their perception of themselves as science people. But why does this matter? By understanding the experiences of first-gen college students in LA-supported science classes, we can improve teaching practices and provide better support for this marginalized group. It is important to note that this goes beyond mere access or academic achievement. It is really about empowering the students to see themselves as capable and confident scientists. To conclude, it is important to recognize that the journey of science identity development is a complex one. However, by understanding the experiences of first-generation students in science classes, we can create a more inclusive and empowering science learning environment. And this, in turn, can lead to a more equitable and effective science education. Thank you.
Hi everyone, I'm Pratik Rai, a first-year molecular biosciences PhD student. The title of my presentation is a strategic design of autotaxin inhibitors through molecular modeling for overcoming cancer therapy resistance. Let me start with the theoretical background of my research. So what is autotaxin? Autotaxin is an enzyme that generates lipid signaling molecule LPA. As you can see from the figure that autotaxin converts its substrate, which is LPC, to the product LPA. LPA induces several cellular responses by modulating 6 distinct LPA-G protein coupled receptors known as LPARs. Since LPA induces cellular responses, this pathway is known as the autotaxin LPAR signaling pathway. Now, what are the chemical signals that we are talking about here? Cells typically communicate using chemical signals, which are proteins or other molecules produced by a sending cell. When that signaling molecule binds to its receptor, it triggers a change inside of the cell. This change is called the response. Cancer cells communicate in the same way for the same reasons. If we somehow can block the signals, then we can stop the tumor cells from performing its usual cell functions. Now, the reason why we are concerned with the autotaxin enzyme is because this autotaxin LPAR pathway can activate several signaling pathways through which cancer cells becomes drug resistant. As a result, by inhibiting this enzyme, we can again make the cancer cells responsive to the known cancer treatments. Now I will explain the methodology that we are following in our research. We initiated with finding the right features in a molecule that can provide better binding with the protein target. This process is called pharmacophoric search. Then we utilized molecular docking to comprehend the protein ligand binding affinity. Then molecular dynamic simulations were performed to understand the protein ligand interaction in conditions which mimic the physiological conditions. Then we utilized a quantum mechanical method which makes use of density functional theory to understand the properties of compounds through atomistic level investigation. Eventually, we selected some compounds for organic synthesis. For synthesis, we utilized a solvent-less blue LED induced green chemistry method in which the blue light was utilized at the source of energy. The compounds synthesized are then chosen for biological investigations. We ran an enzyme inhibition experiment in which we tested our compounds against the autotaxin enzyme for inhibition as indicated by fluorescence. In the results section, as you can see, we were able to visualize and characterize the non-covalent interaction taking place between the protein and our design compounds. From the simulations, we found out the stabilities of these systems. We analyzed the potency of the design compounds first through single dose assay and then through dose response assay. Through these experiments, we found a compound having an IC50 value of 1.6 micromolar. In future, we will be synthesizing the structural analogs of these compounds to bring the potency further up. That was all from my side. I hope you enjoyed it. Thank you for this opportunity. Happy exploring.
Hi everyone, my name is Rahmi. I am currently in my third year of MSc PhD program. My research focus on how students learn evolution. As a biology educators, have you ever wondered if our students really understand the concept even when they get good exam grades? So during the exam, did they answer correctly because they genuinely understand about the topics, or did they just know barely enough to make a good guess? My research aims to improve assessment of evolution by examining students' ability to monitor their own thinking and understanding. For example, if students study for exam and believe they had a strong evolution understanding, but then they answer a question incorrectly, it suggests that they thought they understood about the topic better than they actually did. In education research, we could call this as inaccurate metacognitive monitoring. Previous studies suggest it can lead to believing the wrong information, and if students believe incorrect information, they might not realize their mistakes and continue to think that they are right. So in this study, I surveyed thousands of college students across 11 states. They completed a survey of evolution understanding before and after receiving the same virtual evolution instruction. Students evaluated 14 statements, whether it's true, false, or they can choose I don't know enough to answer. So using this way, we could avoid students guessing and know if they had inaccurate conceptions or simply they just lack of the information. Let's take item 1 as an example here. Prior to learning evolution, 10% of students indicate that they genuinely didn't know about the process of evolution only occurs in population and not in individuals. However, this percentage decreased by 5% in post-assessment. Still, from item 1, we can observe that 30% of students had inaccurate understanding, thinking that they knew about the concept when they actually didn't. And after instruction, this percentage decreased by 7%. So using this type of assessment, we could also identify which evolution concepts are particularly challenging. We found that inaccurate understanding can even increase after learning, which happened with their items in red arrow here. For example, students believe that evolution is progressive, that species evolve to be perfect, natural selection is a random process, and they also had the Lamarckian inheritance conceptions. For all these items, students' inaccurate understanding increase even though they become more familiar about the content. So as an instructor, we can use this type of formative assessment before starting a class to monitor their learning progress. Also, we can use it to evaluate our teaching and find ways to help students better comprehend these concepts.
When you think of math class, what does it look like? For many of you, it might look like this picture. What may look like a simple sketch communicates a lot more about how the artist views themselves in relation to math. For example, in this picture, the teacher stands at the front of the room sharing knowledge with students and desks. But what does the physical positioning of the teacher and the students in the drawing say about how the artist views math, or if they view themselves as a math person or not? This is a question I began to wonder when I taught high school math, and a question I use to motivate my research today. What is the role of the teacher in the student's development of a positive math identity? In other words, does the place of the teacher and students, the discussion, the responses to students' ideas in the classroom, play a role in the student's understanding of themselves as a math person? In my dissertation research, I am collecting video recordings and conducting observations of the interactions in a high school math classroom. I am also interviewing the teacher about their interactions with specific students at the beginning and end of the semester. I conduct beginning and end of semester interviews with the students as well, who I have tell their story about learning math and draw pictures like the one here to address this question. By analyzing this data, I have found that students describe themselves in many ways in relation to math. Students talk about conversations they've had with friends or family about math, discussing different ways of solving problems with their parents as they complete their homework. They talk about liking or disliking math, often describing why they view math as challenging. They talk about it if and how math will be a part of their future careers as anesthesiologists, CSI investigators, basketball players, and more. From the teacher interview, I learned that the teacher makes many different moves in the classroom that may influence students' math identities. The teacher has many different factors that go into why they make the moves they do in the math classroom. For example, the teacher validates a student's idea by coming back to consider it as a class to move the thinking forward. They make this move as a part of their process of ordering students' ideas in a way that structures the content in an understandable way for students. Other moves the teacher makes include reminding all group members to play an active role, or creating a classroom that is a safe space for multiple solution paths. The goal of my research is to make connections between these moves that teacher makes in the classroom and students' development of a positive math identity. You may wonder, why does this matter? Well, many researchers in math education have found that the way the teacher interacts with students in the math classroom influences how they feel about their ability to do math in the moment. My theory is that over time, these interactions compound upon each other until the student says, "I'm a math person," or "I'm not a math person," when asked about math. So next time someone says they are or aren't a math person, try following up with, "What sorts of interactions have you had learning math in school?" You may find that the role of a teacher is a common thread woven throughout these stories.
Hello, my name is Thomas Seaver, and my thesis is titled Development and Assessment of Physically Based Numerical Sediment Transport Models for Shallow Overland Flow. Roughly speaking, this means I study sediment erosion on shallow water flow surfaces. Now, why is this important? So we need to understand soil erosion to protect our economy and our environment. In agriculture, soil erosion will carry away topsoils containing fertilizers and damage crops. So we need to understand where that will happen. We also need to know where those fertilizers will end up, because the water can carry those pollutants downstream. To be able to implement our understanding of soil erosion, we need to construct soil erosion models. These are models which are able to generate maps of where erosion occurs and how strong the erosion will be. Having these maps allows us to develop conservation plans that minimize soil erosion and maximize resource efficiency. And there are issues in understanding soil erosion is that it's a complex three-dimensional problem. When we look at it and try to gather data, it's very difficult to gather the data in a real-world scenario because we often won't be able to have sensors on the field. My objectives in this thesis are to be able to study and evaluate existing soil erosion models, as well as to propose enhancements to existing equations that support the disaggregation of dominant erosional mechanisms that we study when we look at soil erosion. And I'd do this by first taking data from the USDA Advanced Remote Sensing Laboratory, and I use a pre-existing hydrodynamics model to drive my two developed models. The first model I developed calculates topographic change using a set of empirical erosion equations, and the second model uses a set of numerical and empirical equations to calculate sediment transport and erosion. At the top right are the results of my two models, and on the left of that box is the sediment loss. That is how much sediment is leaving the flume at any given time, and we can see my Model 1 and Model 2 both perform fairly well against the observed data. On the right of that is geomorphology, which is how the topography changes in time. And at the final time we have from the observed data, we can see that my Model 1 and Model 2 don't exactly match very well with the observed. And this means that we need to have further work on the development of these models to improve how it matches the geomorphology. To do this, I would need to take Model 1 and improve the equations in it, and I would need to take Model 2 and improve how the sediments are deposited on the bed. That is my thesis. Thank you, and have a wonderful day.